But the question might be, is it really that simple? Is it just that you can map out the network, figure out which nodes to target, and you're done? Um, well, when some very smart physicists started doing this on, for example, the physical topology of the internet, computer scientists didn't really take it that seriously because they said, well, it's how these ISPs or how these different nodes are connected is dynamic. So you have routing tables, and depending on um, where the packets are getting through and where they're not, the routing tables are continuously updated. So you can in fact inflict what you think is a lot of damage, and the network simply organically adapts to what is going on. Similarly, it would be nice, ideally, you map out a terrorist network or a criminal network, for example, individuals involved in the drug trade. However, there was recently a report, the 10-year-long effort by the US to target exactly this kind of drug trade network. And they found that no matter how many of those nodes they removed by incarcerating them, sending them to prison, the network adapted. Just new people came in and filled that space. So it's not that the network is sitting there and saying, oh, okay, I lost this node, I'm not going to do anything about it. They're very dynamic. And so yes, perhaps during a short time period, if you can simultaneously take out a lot of the nodes and the network has no way of replacing them, then you can predict, that you're going to be able to break up the network into small non-functioning parts. But in general, you have to be careful about this particular assumption, what power you have to bring the network down. So let's look at a particular example, and that is of the power grid. Here again, we're going to dismiss some assumptions that we had with other networks, and we're going to introduce some new simplifying assumptions. Here, what we're talking about is that where the electricity is produced is not always where it is consumed, and you need intermediate distribution, actually transmission stations that will bring the power from the generators to the kind of end distribution stations that then deliver the electricity locally to customers. And as you probably are aware, failures of the power grid can be quite dramatic. So if you have a power plant go down or one station go down at one location, you can get what's called a cascading failure, where entire swaths of the country will be without power, because this is a network, and what happens at one node actually influences what happens at to the other nodes. So in a way, here the damage is greater. It's not that removing one node, now you've lost the paths that go through that node and the edges involved with that node. Because electricity flows, basically simultaneously through all possible paths, one removal of one node actually affects all of the rest of the network to a greater or lesser extent. So let's see how that happens. What happens is that when a node goes out, it will have some load and a capacity, and say that the load exceeds the capacity, the node will fail, and now its load is redistributed around to its neighbors. So I'll just follow this paper by Kinney et al., and this is Rekha Albert from the Barabashi and Albert model, who's on this paper as well. So again, the nodes are generators, transmission substations, and distribution substations, and the edges are these high voltage transmission lines. And there are basically thousands of these nodes and about 20,000 edges. So what happens? Well, first of all, you see this straight line and you might think, oh, that's a power law. Well, no, it's not. Actually, the power grid is an exponential network, and you can tell because this is a linear axis and this is logarithmic, and so that means that there aren't really these huge hubs, right? The highest degree node has fewer than 25 connections, which kind of makes sense. Can you really imagine one of these transmission stations being wired to 1,000 others, right? You just can't really imagine this topology of high voltage wires really doing that. So we have an exponential network, and now we need to know where is the electricity flowing. So it's not just that it flows through all paths, so we're going to see which paths is it really flowing through depending on their capacity. And so we're going to have certain efficiency of the edge, and we can compare, and then we have the efficiency of the path that is composed of a bunch of these edges. And the simplifying assumption in the end is that we're going to assume it only goes along the most efficient path, but in practice it actually goes through all of them, but primarily through the high efficiency one. So we can compare three different paths. Path A has two edges, and each of those edges has efficiency 0.5, which gives the efficiency of the path of 1/4. Path B has three edges, each with efficiency 0.5, which gives the efficiency of the path as 1/6. And then path C has two edges, one with efficiency 0 and the other with efficiency 1. And the efficiency of the whole path is 0, because if part of the path lets no electricity through, then that path lets no electricity through. And it's nice that instead of averaging these efficiencies, we have that the shorter path is more efficient. So we can then look at the efficiency of the overall network, and we're going to just look at all the paths between all the generating stations and all the kind of end distribution stations. And we're going to look at the efficiency of the most efficient path between I and J, and that's how we'll measure how well the network as a whole is doing in delivering the electricity. What we're also going to say is that the capacity of each node is proportional to its initial load times alpha, and you want alpha to be greater than 1 because you want its capacity to be greater than its initial load. And then what's going to happen as the dynamics unfold is that if the load is less than the capacity, then the neighbors are unaffected, right? The node is functioning as usual, and the neighbors are just carrying whatever they would normally be carrying. However, if the load of this node exceeds the node's capacity, then that node shuts down temporarily. As long as the capacity, as long as the load exceeds the capacity, it'll be in a degraded state, and instead its neighbors are going to have to carry some of the load, which is going to degrade their efficiency by this factor, which is how much the original node was overloaded. And so this is kind of this distribution which then can produce the cascading failure. One node exceeding its capacity now puts that load on its neighbors, who in turn can fail, and those nodes in turn might then distribute their load to their neighbors, etc. And what in this paper they measured, simulating but on the real topology, is what happens if you just remove nodes at random. So you just assume one or more of them are failed for some reason, and this is as you target, you get to pick which one fails, and you can see that this is worse because the network efficiency drops down further, and this is random. And here is the overload tolerance. So just look at this figure closely and see what you can conclude about the network efficiency as a function of this overload tolerance that you've given to the network. So specifically, the quiz question is, how much higher would the capacity, the average capacity of each node need to be relative to the initial load in order for the network to be basically unaffected by the removal, either targeted removal of a node or a random failure of such a node. So hopefully what you saw was that increasing the average capacity just 30% or 40% above the typical load, what we call the initial load, would render the network relatively safe to the random and even targeted failure of a particular node. Now, why did in the past these cascading failures occur? Well, that was because power companies had little incentive to provide this additional capacity, right? Because they were kind of charging for the load they were carrying, not for additional capacity they could provide, which would kick in situations where there were failures. But research such as this can show that that additional capacity need not be that large, and it would still render the network pretty resilient to failure. Now, to recap, we saw that resilience really depends on topology, and this was not just the degree distribution, which then rendered the network, say, more resilient to random attack if the degree distribution was skewed, but less resilient to targeted attack in that case. But it also depends on what happens when a node fails. It could be that that's it, just the node fails, but all the other nodes are unaffected. Or it can have this cascading effect, for example, what we see with the power grid. Or it can have the opposite effect, which is what we saw with, say, crime networks, where the node is quickly replaced. In fact, someone was probably eagerly waiting to occupy that spot, and so the damage isn't even as bad as, having that node no longer there.